In this video, we'll get some insight into the main thermodynamic processes that we'll encounter, and I'm going to write down our first law of thermodynamics, which states that the change of internal energy is equal to the heat flow in or out of the system, plus the work done on or by the system. And I'm going to write the ideal gas law, because in this course we're really considering an ideal gas as our system. Now, starting off with this green process over here, where we go from state A to state B, and the pressure does not change. So this constant pressure process is known as an isobaric process. So basically, to keep the pressure constant, where we have an expansion, so we had an increase in volume from state A to state B. So in other words, the piston moved upwards, which would result in a reduction of pressure. So basically, we'd need heat input from this reservoir to keep the pressure constant. So therefore, for constant pressure, if we turn this equation around, we have the volume is equal to nR on the pressure multiplied by the temperature. And given that this quantity is constant, then what we have is the volume is proportional to the temperature, or the volume on the temperature is constant. Meaning that the ratio of the volume to the temperature in state A is equal to the ratio of the volume to the temperature in state B. And this here is known as Charles's law. Now, looking at this blue process over here, so we go from state B to state C, where the volume is constant. So this is called an isochoric process, where the volume does not change. So therefore, because the volume of the gas does not change, then the work is effectively zero. And therefore, the change in internal energy of the gas is completely due to the heat flow in or out of the system. So therefore, because the volume is constant in this case, then what we have is the pressure is equal to the number of moles of gas by the universal gas constant on the volume multiplied by the temperature. So what we have in this case is the pressure being proportional to the temperature of the gas, or the ratio of pressure to the temperature is constant, meaning that the pressure on the temperature in some state A is equal to the ratio of the pressure to the temperature in state B. And this here is known as Gay-Lussac's law. Now, our third main process is where the temperature is constant. So this here is called an isothermal process. And in an isothermal process, where the temperature is constant, well, the change in energy of the gas between two states is zero. So remember that by Joule's experiment, the internal energy of a gas depends on the temperature. So if the temperature is constant, then the change in internal energy is zero. And this means that the sum of the heat flow in or out of the system plus the work is equal to zero for an isothermal process. So if the temperature is constant, well, what we have is pressure is equal to nRT on the volume. And given that the quantity of the numerator is constant in this case, well, what we have is the pressure being inversely proportional to the volume of the gas. And therefore, the pressure multiplied by the volume is constant, which means that the product of the pressure and the volume in state A is equal to the product of the pressure and the volume in state B. So in other words, if the temperature is constant, then the internal energy does not change. And this here is known as Boyle's law. Now, there's another process that needs some calculus to derive, but we'll just look at it qualitatively. And that's an adiabatic process. So in this case, there's no heat flow in or out of the system. So we insulate the entire system such that Q is going to be zero. And therefore the change in internal energy is equal to the work done on or by the system. So you can imagine if we compress this piston, that's going to increase the energy of this gas. So the molecules are going to bump into the walls more often, they're going to have a higher kinetic energy, and therefore you get a positive change in the internal energy. And doing some calculus, it can be derived that the pressure by the volume to the power of gamma is equal to a constant, and gamma is the ratio of specific heats at constant pressure and volume. So an adiabat looks similar to an isotherm. So if you rearrange this equation, you'll get P is equal to a constant on V to the gamma. And if gamma is equal to 1, you'll have a similar curve to the isotherm over here, as we've derived for this case over here for a constant temperature process. So these are the main processes that we'll encounter in this introductory course on thermodynamics. And I'll see you in the next video.